and take the constant level of this function, say we fix z equal to a, so we have a plane which so here is the level set. Level set on the x1, x2 plane will be something like that. Okay. Then what you suggest, Michailo, is that we should, if we have here a point x0, then we should draw a tangent line to that. This is a plane.
No, it should be a tangent plane.
Tangent plane here.
Yes, as a function.
Here. Well, you are complicating already things. It's very difficult for me to draw a tangent plane here. But let's stick to that actually. So look, if you want to compare the value of the function at some close point, say we take x here and we compare the values. So if this, okay, I should have probably draw it on the front so you could see what happens. So if we have here our x0 and there somewhere the other point x. How can we compare the values of function f here and there? So here we have this red point here. So this corresponds to the value of that function. And then we have another point, well, and it is somewhere here. It's probably higher on this function. How can we compare it? Well, we know that up to the second order correction, this is the gradient of f at the point x0 times the increment plus something which is of smaller order. So what we have here is a linear term plus correction. Let's ignore it for the moment and just understand when at least the values of f are larger at the point x than at the point x0. Well, everything depends on the sign of this term, because as we said, this is the leading term. The correction will not affect the sign in small neighborhood. So when is this term positive? What do we have here? Gradient is a vector, and this increment is a vector. These are vectors in R2. In our case, but in Rn in general. If you have n variables, then the gradient is a vector in Rn, and x's are in Rn, so we have the scalar product of two vectors. When is the scalar product positive? When the angle is acute. So less than pi over 2. It is 0 if they are orthogonal, and this becomes negative if the angle is indeed greater than pi over 2. So now what you said about the tangent line makes perfect sense, because what we have actually is that the tangent line to this level set will be orthogonal to the gradient. We'll derive this in a second. So actually our gradient will be orthogonal to the tangent line. And therefore, if our level set is convex and we have x, so if this angle is less than pi over 2, then we see that this becomes positive. So basically, in the half plane, half space, which is in the positive direction of the gradient, the values of the function increase. Well, this is of course local, but this is so. And on the contrary, if we go into the opposite direction, so if you consider the other part, so say points somewhere here, then because every increment will form obtuse angle with the gradient, this scalar product will be negative, and therefore we will be decreasing the value of f. And now it is clear now why the gradient is precisely the direction of the fastest growth. Because if we want to increase our function the most, and we only are able to make step of fixed length, some small step, in which direction should we point it? Yes, we know that the scalar product of these two vectors is the product of their length times the cosine. So we want the cosine to be the maximal one, and this is precisely when the direction of this increment coincides with the gradient. So if we are allowed to make a small step of length epsilon, for instance, then the direction along which we will increase the function at most will be precisely the direction of this gradient. Now another thing about this level set, why the gradient is orthogonal to the tangent line to the level set. Look, if you have a level set of a function, so this is the set of the form f of x is equal to the fixed value c. We take any point here, so this is our point x naught, and we draw a tangent line and the gradient. Then it turns out that the gradient is orthogonal to the tangent line. Why is it so? Well, look, what we can do, we have this level set C capital. Yes. What we can do, we can, roughly speaking, go along this level set in some direction. So we form a function x of t on C, on the level set. Then f calculated at these points by definition is constant. It's equal to that C. But this is a function of scalar variable t. Because it is constant, its derivative at every point, in particular, let's assume that x naught corresponds to x of 0, for instance. Yes. So then, if we calculate g prime at 0, this is the derivative of the composite function, and so this is actually directional derivative of f in the direction along which we go around this level set. So this will be the gradient of f at that point x naught times the derivative okay, so I'll take any t naught. No, not any. If this is 0, then I should take 0. Sorry. So once the derivative at 0 will be the gradient at x naught times the derivative at 0 of this x. But the derivative at 0 of this x is precisely the momental acceleration velocity, and this is the tangent to that curve. Therefore, we have the product of two vectors. One is the tangent to that curve at the point x naught, because we are going along that curve, and the other is the gradient. And the product gives us the derivative, and the derivative of that function is 0 because it's constant on the level set. That's why the gradient is indeed orthogonal to the tangent line of this level set. We'll use it later, so that's why I stop at this this detail. Okay, good. Look, another property, interesting property of the concave functions is that the so-called upper the set of this form. So we consider all x's for which the values of f is greater or equal than the value at x naught. This is sometimes called an upper graph of upper set of the function. It is then the convex set. Look, here is the picture. If we have a concave function here, concave function, and we fix some value and consider the level set. So this is the same picture, but in the this second plane. Then all points inside this level set correspond to the larger value of the function. Therefore, this epigraph, upper part of the function at that level value is a convex set. This is typical for, this is general property of a concave function. For convex, we will have the bottom of the graph, which will be the convex set. And the proof is very, very simple, and it is very easy to see on the picture. If you just take any 2 points here, draw a line, then we see that on this graph we will be going along this path on the graph, and therefore the values will be larger or equal, and that tells us that that all points on this segment correspond to the values of the function larger than on this border, and that's why this holds. Okay, so this property of the function. Good, and finally, so a few examples. Actually, these concave and convex functions arise very naturally when we minimize or maximize some linear functions. Well, for instance, let's consider the expenditure function, which depends on two variables, p and u, where u is the utility which we want to achieve. So we consider x's which return us utility larger or equal than this given set u. And what we maximize, we maximize the minimal amount which we need to spend to achieve this utility. So if x is our spending vector, which has its entries are just the number of goods, different types of goods we want to buy to achieve this utility, then the minimal amount of money we have to spend is just the total price we will pay. Yes? So if P1 is the price of the first type of these goods and so on, then the total price will be this linear function. And so the task is to minimize the cost of achieving the corresponding level of